Okay, so last time we did a little bit of an overview of just various aspects of neuroscience. And then after that, we kind of just started off with a discussion of what 1D flows can look like, what a dynamical system can be, and what does it mean if you have like a 1D flow, which is just some x dot is equal to f of x. And one of the goals for today then is now to start thinking of actually using 1D flows, and then we'll eventually move to more complicated things as well to start modeling particular things in neuroscience. So the first thing that we're going to just be thinking about again is this whole idea of an action potential, right? So just to remind everyone again, what is an action potential? So an action potential is essentially this idea where we know that neurons membrane essentially lives at some kind of resting potential, as shown over here. This is some resting potential. Um, and if I give inputs that are small perturbations to this resting potential, then I would just come back to this resting potential, right? So, in the language of dynamical systems, or in the language of, say, even the 1D flows that we talked about so far, this resting potential, if I think of my voltage as being the relevant dynamical variable, then this resting potential is like a fixed point, right? So, if you remember, we talked about in last class, we also talked about fixed points, right? And we had said that, okay, if x dot is equal to 0, that is f of x is equal to x dot is equal to 0, that is when the f of x curve intersects the x-axis, you get objects called fixed points, right? And these fixed points can be stable or unstable depending on the slope of this curve, right? And so in that language, one would perhaps expect to be able to construct a dynamical systems model where the resting potential, we kind of want this to be like a stable fixed point. Right? This is kind of what we would expect to be able to come up with in the context of a dynamical systems model. Um, that's why any small perturbation should come back. But the other aspect that we also need to capture is that there is a threshold, which is to say that if I happen to give you a perturbation, or if I started off somewhere above my threshold, then I should instead fly away very rapidly. Right? That's what an action potential was. If I gave some perturbation above some threshold, then my potential just continues to increase and moves far away. So one might intuitively then think perhaps that this threshold over here should be like an unstable fixed point, right? And if I am able to set up things that kind of look like this, then perhaps I will be able to capture some aspect of these dynamics, right? So that's going to be kind of like our motivation. And so the way that this is done is the standard model where people kind of think of this is what's called the quadratic integrate and fire neuron. So, okay, so what is the quadratic integrate and fire neuron? It's a very simple kind of model. As I said, the dynamics are in terms of the voltage. So instead of doing x dot is equal to f of x, we have v dot is equal to f of v, right? And particularly, I'm going to say that f of v is equal to v square plus I, where v is, well, it's the same membrane voltage, and I is now some sort of inputs or some sort of input current. Okay. Let's just call it inputs for now. So, okay, so let's try to understand this model and try to make sense of is this actually able to capture the kind of qualitative dynamics that we wanted to describe, right? Okay, so once again, let's take the graphical approach. As we said, we are interested in these graphical approaches. So let's again plot f of v versus v. And now I as an input is a parameter in my system, right? This is some parameter. So let's just examine what the dynamics look like for different values of this parameter. So let's consider three cases. Let's consider I less than 0. Let's consider I equal to 0. And let's consider I greater than 0, right? Okay, so what is this curve going to look like? If I is less than 0, then v square plus I is going to look like this. right? It's quadratic with some part going below, which means right away that I have two fixed points, right? Um, that is this fixed point over here and this fixed point over here. Um, can I guess someone tell me which of these is a stable fixed point and which of these is an unstable fixed point? Actually, is there a mic in the classroom that can be passed around as well? Or is it only the one mic that Deepesh has?
There is a mic.
Okay.
One on the right is unstable.
Yes, the one on the right is unstable and the one on the left is stable. I guess because I'm also on Zoom, I can see some people's comments on chat as well. Yes, the negative slope fixed point is a stable fixed point, right? So this is now stable, which you'll typically represent with a closed circle, and unstable, we will typically represent with an open circle, right? Okay, so what the dynamic going to do over here, the dynamics are going to be the following. Like if I give you any input over here, I'm going to move towards this stable fixed point. So if I start off at the stable fixed point and I give small perturbations, I'm just going to come back to the stable fixed point, right? So this now acts like my resting potential. And this is now going to act like my threshold. Why is this my threshold? Because if I now gave you a perturbation that was large enough to exceed the threshold, then I would insert flyway to this direction, right? So this in itself is already kind of capturing this kind of idea of an action potential. But there's something missing in this picture, right? Like okay, so is this completely capturing the action potential, or is there some aspect of this that we've not yet accounted for? So we have a resting potential. We've said that if you increase above the resting potential and you increase above the threshold, then your voltage increases very rapidly. What else do I need to be able to kind of describe the full action potential idea?
The hyperpolarization phase.
Yes, I need this phase of things actually coming back down, right? I need actually things to they go up and I want them to be able to come back down and actually reset, right? So in a sense, this dynamical system in itself has only really captured this part of the action potential, right? It's only captured this part of the action potential. It's only saying that there's a threshold and then things are going to fly up. Is it possible, if I only have this one-dimensional flow, is it possible for me to also capture this part over here? Can I also capture this part over here in a 1D flow? Can anyone guess how we might be able to capture it? So I guess the short answer is that we cannot. And I guess one easy way to see that is that if I am to capture this at the same value of voltage, let's pick 0 volts, for example, I both need V to be increasing and V to be decreasing, right? So V to be increasing would mean V dot is greater than 0. V to be decreasing means V dot is less than 0. And so I just can't do this, right? And so over here, I'm only able to capture this one phase of an action potential. What we can say is that if, hypothetically, if we could insert some reset dynamics, so that if the V goes very large, I'm going to take this voltage and I'm just going to throw it back somewhere, right? Let's say I could do this, right? Okay, I clearly cannot do this in a 1D flow, but let's say I could do this. Then I will now at some level be able to capture the full action potential dynamics, where it rises up. Once it's pushed above the threshold, it rises up, and then it resets and comes back. Right. So then when you basically do this aspect as well, when you do this resetting as well, this is what collectively one then calls a quadratic integrate and fire model. Now, I can also tell you quickly what happens when I is less than 0 and I is equal to 0. So when I is equal to 0, this is just going to look like this. And so then I have a single fixed point at 0. But this is a fixed point with marginal stability. It's a semi-stable fixed point because it is stable in this direction and it is unstable in this direction. So it's kind of like a weird edge case in the middle. And when I'm over here, when I is greater than 0, then my dynamics are always just going to be with V increasing, right? And if I had this reset, then this will now be just simple periodic activity, right? Because this will now just it'll keep firing and then resetting and firing and then resetting and so on, right? So we can kind of think of this interpret this I inputs in two ways. One is, as we were describing over here, I can think of taking an initial condition and I can talk about what happens if I perturb it to a different initial condition. Or alternatively, you can just think of this as the current input into the neuron. If I have negative current or if I have no current, then also I just sit at some resting potential. But if I am continuously injecting current into my neuron, that injected current is continuously going to keep uh, pushing the membrane voltage above these thresholds in a sense. And so I will just continuously get periodic spiking as long as my current is on. Right. So there's like different ways in which I can kind of think of how to describe this system. Okay. One way that people also kind of try to represent this information, right? Just this is continuing on with the QIF neuron, is in the form of what's called a bifurcation diagram. So what is a bifurcation diagram? This is a thing that we will use repeatedly, so we can just do the first case a little bit slower and more pedagogically. A bifurcation diagram is basically where I am plotting fixed points of a system, or in general attractors of a system, but we haven't talked about other attractors so far. So let's just think of fixed points of a system, which I will represent by V star, as a function of whatever hyperparameters I have to describe my dynamical system. So in this case, we just have a single system because we said V dot is equal to V square plus I. I have a single hyperparameter, I, and so this is the only thing that I can vary against. And so a bifurcation diagram is basically trying to ask for different values of I, what do these fixed points and fixed points look like, whether stable or unstable, irrespective of that. And so what hopefully you can see over here is that these two fixed points are basically going to appear. So fixed points are basically going to appear at V star is equal to plus or minus square root of, square root of absolute value of I, right? Maybe we can just write it as minus I. So that's where my fixed points are going to appear when I is less than 0, right? And then over here, I have no fixed points. So corresponding this figure, what we see is we have this kind of quadratic curve over here. So this is a branch of stable fixed points. This is a branch of unstable fixed points. And on this side over here, I have no fixed points. Right? So this is now the complete bifurcation diagram of the quadratic integrate and fire neuron. So in general, yeah, we will use solid lines to represent stable branches or stable fixed points and dotted lines to represent unstable branches. Okay. Okay, so this is basically a bifurcation diagram. And the interesting thing is, as I've been trying to harp on so much, is that the goal really is that we can do a lot of these things from this more geometric perspective without having to solve a lot of these equations, right? So you might say that, oh, look, this quadratic integrate and fire neuron as written over here, this is an extremely simplistic model, right? Sure, it captured some qualitative aspects, but can we be sure that a more realistic model would also be able to capture similar dynamics, right? Or is that something that I can't necessarily say? And so one example of a model that I won't go into too much detail about this, except for just giving the geometrical picture, is people say, okay, let's maybe look at things in a little bit more detail, and let's do what's called an exponential integrate and fire neuron. So this was QIF, this is sometimes called EIF. Right? And so this is now a more realistic neural model. This is motivated by some slightly more aspects of neuroscience. And as I'll show you in a moment, this actually can also fit experimental observations more directly. But hopefully we'll be able to see that you don't actually need to understand the details to understand the dynamics, right? So the exponential integrated and phi model basically looks something like this. It has a bunch of more parameters, but let's not worry ourselves too much with the interpretation of each of these. Exponential of v minus v theta over k plus some I. Okay, so this is a more complicated model. This is called an exponential integrate and fire model. And just to, I guess, jump a couple of slides ahead, this you can actually see that if I were to look at some experimental observations, actually, wait, let me maybe just try to sketch this out and then it'll be easier to see what's going on over there. So, okay, so let's just go back to this equation for a moment and let's just try to sketch it out, right? So one key skill in the art of dynamical systems is certainly sketching out functions. So let's just see if we can quickly just guess at how I would sketch out this function. Some of you may not, I mean, it takes a while to kind of develop this skill to be able to just sketch out functions very easily. But it's a very, very useful skill, not just in dynamical systems, but in all sorts of areas. So let's just quickly think about how we might do it. So we have a negative linear term and we have a positive exponential term, right? So that's the two core components that we have going on over here. Just this term over here would look like exponential growth. Just this term over here will just be like some sort of negative linear, just a negative linear function. So now when I add both of these two functions up, we know that on this side, in the positive v side, exponential growth is much faster than just a linearly decaying function, right? So that's going to win out, right? So on the right side, I know I'm going to have something that's essentially like exponential growth. On the left side, my exponential function just goes to 0. But here my linear function is actually going to now dominate. And so I know my function must then look something like exponential on the right side, but something like this linear model on the left side, right? So let me actually just try to draw it a little bit nicer. So I basically have something that will look exponential on one side, but look linear on the other. Right? So I'll have something that looks like this. And this is once again in my v dot versus v. And now that just leave this one I, we talked about the exponential and the linear part, all I is going to do is that it's going to move this function up and down, right? So hopefully you can imagine that there will be some value of I. It need not be I equal to 0 like in QIF, but there'll be some value of I such that if I is greater than some I naught, it will look like this. But if I is less than some I naught, then instead I'll have some sort of intersection over here, right? And I'll have this nature of a stable fixed pointer and unstable fixed pointer. Right? So I can have a much more complicated neural model, but just motivated by the same graphical approach, I expect that it will give me qualitatively similar dynamics. And so you can do the more classical modeling kind of perspective where you say that, oh, I'm interested in all of the details. And depending on what you're trying to solve, that might be useful. But so like over here, you can see like actually if you take experimental observations, sometimes depending on the kind of neuron you're trying to record from, it can actually fit this exponential integrate and fire pretty well. But hopefully, I've been able to convince you that you don't actually need to care about the details to understand that this is going to be sufficient to give me some sort of action potential, right? So that's kind of like what is the advantage of trying to look at systems in this kind of fashion. Oh, so before moving on to other aspects of 1D flows, I just want to say a quick thing that like doing this resetting over here is kind of like what you get, kind of like adding an extra dimension, right? So we kind of argue that okay, if I had only one dimension, I wouldn't be able to do this. And kind of we can see that, oh, if I had one extra dimension to play with, then I might be able to set up this resetting, right? And so we can ask, okay, how do I actually go about setting up this kind of extra dimension? And we'll do this more formally later, perhaps later in this class itself. But we can do it kind of heuristically in a fashion where we say that, you know what, The problem that I had over here with resetting is that my real number line, when things went to infinity, they didn't come back, right? So if instead my dynamics lived not on the real number line, where if things go to infinity, they can't come back, but if instead my dynamics itself were described on a circle, then I will automatically have some sort of resetting, right? So if instead of doing v dot, right, if instead I had some sort of theta dot, right, where theta is now some angular variable, um, theta dot being some f of theta, then all of my dynamics live on a circle, and I might have some capability that, if I fly away, I can actually um, come back to where I started in some sense, right? So I won't spend too much time talking about this, but this is basically called a theta neuron model. And I'm just going to state the equation over here, and I will leave you to kind of estimate exactly where the fixed points, the stable fixed points and the unstable fixed points live, or at least argue it out. I'll just sketch it for you. So the model basically looks something like this, where all of my dynamics now live on a circle, and I won't prove it to you, and I'll leave it to you to try this out at home. But if I now just look at my space, my theta space for I less than 0, I greater than 0, well, I equal to 0, and I greater than 0, you actually get some qualitatively similar things, where you get, for I less than 0, you get a stable fixed point and an unstable fixed point. Here you get a semi-stable fixed point, and here you have no fixed points at all. And so here I just keep cycling around, which you can think of this as spiking and coming back from spiking. And if I'm over here, I have, once again, I have a resting potential. And here I have a threshold for firing. So if I give small perturbations, I'll come back down. If I give large perturbations, then I will kind of fly off to quote unquote infinity. And then I will be able to reset on my own. Right? So this is kind of where you can change the topology of the space to kind of help me with the resetting. But I won't spend too much time in describing all of this. I will leave you to looking at various textbooks for this. So if you look at the Izikevich textbook, you can find the full title. I'll share the slides with everyone. But if you look at the Izikevich textbook, you look at sections. You look at section 3.38. You will have more of a description of what it means to be able to set up something like this. So this is called a theta neuron model. One more aspect I should just say in terms of terminology is that this particular style of bifurcation is given a term. This is what is called a saddle node bifurcation. This particular style of bifurcation where you have a stable fixed point colliding with an unstable fixed point and they both vanish. That's called a saddle node bifurcation. Correspondingly, you can see we have something similar happening over here. I have a stable fixed point and unstable fixed point that collide. So this is also a saddle node bifurcation. But all of the dynamics are happening on a circle. So this is called a saddle node bifurcation on an invariant cycle. Or it's also called a SNCC bifurcation for short. This is just in terms of terminology. If you're reading the textbook, just having this terminology at the back of your mind will just be helpful as you go along. Okay, yes. So this is basically one classical type of bifurcation that you can get in one systems. And we can see right away that this bifurcation is actually can be very helpful in me thinking about neural dynamics. Okay. Let me maybe take a pause here for any questions, and then I can move on to other things that we can model with 1D neural dynamics in the context of neuroscience. Are there any questions?
Hi, sir. I had a question about how you assume the topology of like. So you assume that that the neuron is on some sort of sphere, right? And I was
Uh,
wondering if the choice of a sphere is arbitrary. Like, can you do it on any given space, or?
there's no sphere over here. Do you just mean the circle over here?
Yes, sir. Yeah.
Yeah. So, well, okay. You can certainly cook up dynamics on any arbitrary manifold, right? Which could be a circle, a sphere, a torus, whatever you'd like to. I mean, of course, the question then is like, what are the ones that might be useful for the kind of system that you're trying to model? In this particular case, just motivated from the fact that we wanted some resetting to take me from things flying off to large voltages and come back. That kind of motivated the choice of thinking about things on a circle. You can model different kinds of dynamical systems on other manifolds, and there are neuroscience relevant dynamical systems as well, that can be modeled on these higher dimensional spaces as well. So we will look at dynamics on more and more higher dimensional spaces as we go along in the course. Right now, this choice of circle was motivated from the kind of system we were trying to model, which is to say that a potential that flies up actually gets reset as well.
So could we similarly just choose a torus instead? Because that whole we can just like define a square, and we can just load the edges and that kind of
Yeah, sure.
thing.
You could define dynamics on the torus if you have something like, okay, a circle is like a one-dimensional torus in a sense. Like a torus is more useful if you have more than one dimensions, if you have a variable that lives in more than one dimension. And eventually we will write out systems where it will be useful to think about more than one dimension. Maybe you're just thinking of two neurons instead of one neuron, right? Then it can start being useful to try to model dynamics on a torus rather than just on a circle.
Okay, thank you, sir.
Yeah. Are there any other questions in the classroom?
No.
Okay. I can see that there's something on the chat. Uh, what do you mean by resetting? So by resetting, I just mean this aspect of like the potential being able to come back down. Which is to say that after the voltage increases, I want somehow my potential to again return to my stable fixed point of my resting potential. And so similarly over here, I meant that if I had dynamics where my potential, if it continued to increase, if I could somehow artificially reset it, artificially bring it from this high value to a small value, then I will achieve that similar kind of resetting. And that's kind of what we argued we can achieve on a circle. Okay, if there are no other questions, are there any other questions?
No.
Okay, so then let's move forward with some more examples of one-dimensional flows or one-dimensional bifurcations, and see what kind of neural systems they might model, right? Um, One more thing that I'd like to say quickly before that is that this saddle node bifurcation that I wrote over here, hopefully you can agree that this kind of dynamical system is possibly one of the simplest versions of a dynamical system that can give this. Now we wrote an exponential integrate and fire model that looks kind of more complicated, but I won't go into too many details. But hopefully you can see that at this I equal to I naught, when my curve looks just like it's just touching the x-axis, I can kind of expand, do some Taylor expansion about this point, right? Because this has some minima, I can do some Taylor expansion and the dominant term will be a quadratic term, right? And then my varying my current will take this quadratic term and move it up and down. So in a sense, if I were to say that I'm only interested in values of potential and current that are very close to this point, the point where I'm just touching, then I can kind of approximate the system with the same dynamics over here, right? And so as a result of that, we actually call this particular form over here, this is called the normal form of an SN bifurcation. This is the normal form of a saddle node bifurcation, which is to say that even if I had a more complicated dynamical system that qualitatively did the same thing, I could probably zoom in enough and do some change of variables and do something and reduce it to this equation, right? So that's why we call it the normal form. And so oftentimes the dynamical system, we're really going to be interested in thinking of things at the level of normal forms with the idea that, okay, this is one simplest example of a system that does some phenomena. There probably are several other complicated systems that also show the same phenomena, but I can kind of do some change of variables and zooming in enough to just reduce it down to the simplest version of the equations. So oftentimes we'll just look at some simplest version of the equations. Okay. So, okay. So with that motivation, let's now try to write out some other kinds of bifurcations that you can get. And so we'll just do the two classical kinds of bifurcations that people look at in 1D flows. Just one is the first is going to be a transcritical bifurcation. Okay. So what is a transcritical bifurcation? Let's not worry about the jargon in the dynamical systems language. Let's try to motivate it from a neuroscience example, right? So let's say I'm interested in modeling what are called avalanche dynamics. So what are avalanche dynamics? Avalanche dynamics are basically something like this. Let's see if I can do that. Yeah. So avalanche dynamics is a slide I had kind of shown earlier as well. But avalanche dynamics are basically I have some set of neurons that are all coupled to each other. And the idea is that if one neuron turns on, it has some likelihood of trying to turn on other neurons. Okay. And so what you can see in this animation, this is actually from real data, is that sometimes, sometimes if a single neuron turns on, right, if a single neuron turns on, it then can make some other random neurons turn on as well, right? And so this can lead to a cascade of activity, right? This could make this active, this could make this active and this active, which could make this active. This might make something else active and so on. So this leads to like a cascade of activity. Or well, like an avalanche of activity, like some small perturbation. I think someone brought this up in Monday as well. Like some small perturbation might be able to give rise to a lot of other perturbations. And this is what one calls an avalanche, a neuronal avalanche. Okay. So how might I I'm going to give an extremely simplified version of a neuronal avalanche, just because, I also want to just think about 1D flows right now. So it all comes down to a different scale of modeling, right? We talked about what is the level of abstraction of modeling that we might be interested in. Here, so far, we've looked at modeling of like action potentials, and we reduced action potentials to the one periodic variable. Now let's talk about this more abstracted perspective where I'm just thinking of like, are neurons on or off? And in fact, all I'm going to say I'm interested in is some variable A, which is just the fraction of on neurons. So this is just like extremely coarse-grained. I say I have this entire system which has some fraction of neurons that are active. So this A is going to be something that lies between 0 and 1, right? Either 0 are on or 1 are on, right? One important thing to note is that A equal to 0 is what's called an absorbing boundary condition. So what do I mean by that? I mean simply that if my system goes to zero activity, literally zero activity, A is equal to 0, then my system is just going to stay there, right? I can't possibly have, like, this is some system where I'm assuming that there isn't some random fluctuations in the quote unquote environment. I'm trying to model all of the neurons. And so if nothing is active, then everything remains put, nothing happens. And so we expect A equal to 0 is a fixed point, right? Do we expect this to be a stable fixed point or an unstable fixed point? Hopefully people in class are saying unstable fixed point. Okay. So why is it an unstable fixed point? Because we expect that any small perturbation should give rise to a lot more activity, right? So we want some dynamics where I'm probably expecting this to be an unstable fixed point. Okay, so let's try to write out what a dynamical equation for this might look like. So first of all, I say that my A dot, I want to say that there's so neurons, when they fire, they also like spiking is a short thing. It just gives out a burst, which can give rise to more activity. But overall, there's going to be some aspect of like a decay in activity. Like if my neurons were isolated, then things will just have some decay over time. But this decay is, of course, being counteracted by the coupling between neurons, which is giving rise to more possible activity, right? And so simplest possible description of this coupling can look something like this, where we say that the activity growth is basically proportional to the fraction of active neurons. Right? The more neurons that are active, the more they can make other neurons active. And it's also proportional to the available fraction of neurons, right? How many neurons are there that I can activate potentially? Right? So I get something that looks like A dot is equal to minus A plus lambda A times 1 minus A. Right? This is, of course, an extremely simplified dynamics. You can do this in far more complexity, and this relates to all sorts of interesting fields of physics like percolation theory and so on. But I'm not going to go into that. Let's just simplify this equation instead. So if I just were to simplify this, this just gives me A times lambda minus 1 minus lambda A square is equal to A dot, right? Okay, so A dot, let's maybe write it as dA dt. You'll realize why in a moment. So this is dA dt. Let me divide all sides by lambda. So I have dA by lambda dt is equal to A times lambda minus 1 upon lambda minus A square, right? Now, if I'm in general interested, once again, this qualitative nature of the dynamics, right? What are fixed points? What are unstable fixed points? What is stability? What is not stable? I can always rescale time, right? I'm just interested in if something is stable or not. Then if it goes very fast to that fixed point or slightly slower to that fixed point, doesn't really matter, right? So then I'm just going to rescale time. I can define a new variable t to be just lambda times t. And so then my equation then with respect to this new variable time is just A dot is equal to A times some lambda minus 1 over lambda minus A square. Okay. This is, okay, let's just add a slide over here. Yeah, so let's just copy that over here. So we have A dot is equal to A times lambda minus 1 over lambda minus A square. Let me just call this quantity over here to be some mu, which is now, so now I finally arrive at a very simple looking equation. A dot is equal to mu A minus A square, right? So let's try to sketch this out and try to understand what might be happening, right?
Sarthak, there's a question.
Yeah.
So what is the physical motivation of having the decaying term minus A?
Yeah, the physical motivation for that minus A, this is kind of just capturing the aspect. So I'm thinking that a spike in itself, if my neurons are isolated, right, then any neuron can turn on, which is like, okay, I have some set of active neurons, say I have fraction A of active neurons. That set of active neurons is going to decay over time, in the sense that my neurons are not going to remain active, right? So my minus A is just kind of capturing the fact that, okay, neuron spikes are these intermittent things, activity, right? And then over some time scale, there's going to be an effective decay. And then the second term is the growth for how the neurons are now coupling to each other.
So that is just capturing the kind of the post-threshold region of the action potential.
Yeah, you can think of it like that. Absolutely. Yeah.
I have another question. So we've modeled the decay just as minus A, but what about like inhibitory connections between neurons? Because we're trying to model an avalanche, and if the excitations are modeled in the growth term.
Yeah.
but the inhibitory connections could also contribute to the decay of activity.
Yeah, so that is a great question. Um, so okay, so the two things, two responses to that. First of all is that you can actually have avalanche-like dynamics happening in a bunch of excitatory neurons itself. Um, and the reason why everything need not blow out to infinity is because every neuron does not, as we talked about last time, it's not like it deterministically activates other neurons, right? So every neuron has some, you can think of it as some probability to activate other neurons, right? And so just even in purely an excitatory setting, you can still get a sense of avalanches which can decay over time as well, just from this probabilistic aspect, right? You can say that, hey, I also want to model inhibitory neurons, and of course, you can, as I said, you can certainly model avalanches in far more complexity. This is just like an extremely simple version of what the dynamics might look like, just to kind of motivate some simplified version of these different kinds of bifurcation diagrams. But it's certainly a valid level of abstraction. Like at a certain level of abstraction, this is a perfectly valid description of the dynamics.
Yeah.
Yeah. Anything else?
You can continue.
Okay. Yeah. So okay. So what you get in this picture? Okay. Let's do that again. Yeah. So this is again looking at A dot versus A. We can once again think of the different regimes. Let's think of mu less than 0. And mu greater than 0. And you can say intuitively that this basically corresponds to lambda less than 1 or lambda more than 1. So if mu is less than 0, then I will basically get something that looks like this. This is again going to be a quadratic function. But the special thing that you can see over here is that a equal to 0 is always a fixed point, right? This is what we argue, that a equal to 0 is an absorbing boundary condition. So here, this is a stable fixed point, and this is an unstable fixed point. Whereas over here, you have a quadratic that looks like this, where this is a stable fixed point, and this is an unstable fixed point, right? So I can once again draw a bifurcation diagram of this mu parameter, or you can think of this as being like, this is basically talking about mu with respect to 0 is similar as lambda with respect to 1. And so we can again mark out my fixed points. And what you'll basically get is, for mu less than 0, a star equal to 0 is a stable fixed point. But for mu greater than 0, it's an unstable fixed point. But I also have this other fixed point over here, which, okay, if you calculate it out, hopefully you can convince yourself that this is just at a star is just equal to mu over here. So I have another branch over here where this is now a stable fixed point. And this is now an unstable fixed point. Right? So earlier we had this sense where a stable and unstable fixed point collided and they vanished. Here you have a stable fixed point and unstable collide, but they just exchange their stability. Okay. So when you have a dynamical system that does something like this, this is undergoing what's called a transcritical bifurcation. Okay. Yeah, so this is just another example of a bifurcation. Let's do one more quick example of a bifurcation system before we now then move on to two-dimensional dynamics and start adding more complexity to what I can do, right? So what I'm going to now describe next is what's called a pitchfork bifurcation. Also, I should just remind everyone, in case it was not obvious, that the reason I simplified this so much is that this is now the normal form of this bifurcation, which is to say that several other systems which show this kind of exchange of stability, which are not just mean field avalanche dynamics, but are also other kinds of dynamics as well, will all at some level be reduced to some sort of functional form that looks like this. Right? Okay. Yeah. So just getting back to pitchfork bifurcations. Here let's approach this a slightly different fashion. Let me first give you the normal form, and then kind of explain to you why it might have some neuroscientific relevance. So let's consider a normal form that looks like x dot is equal to mu x minus x cube. Okay. So what's going on over here? Let's once again just sketch it out for different values. So you have x dot versus x. This is going to be for mu less than 0. Well, sure. Let's also do mu equal to 0. Why not? For mu greater than 0. Okay. So once again, let's put our skills at sketching functions to handy. The dominant term over here is a cubic term. So we expect, and it's a negative cubic term. So we expect that in all of these cases, at plus infinity, I am somewhere very negative, and at negative infinity, I'm at somewhere very positive, right? So we know our function is going to look like that, and that must be true in all cases. Now, how does it connect in between? So we know it's a cubic function, so it's going to have some sort of cubic-like structure. If my mu is negative, then here, both terms over here around 0 are both contributing to it being negative itself, right? So here also, I think my system is going to just look negative, right? And so then my system overall, hopefully you can then intuitively see that it's just going to look something like this. Something like that. Right? Because it has to kind of satisfy all these different, I mean, the way to just think of sketching out all these functions, just think of different example cases and see what's going on, right? Here, we're going to get something similar, but you can see the slope at 0 is going to be 0. So it's going to do something like that. Whereas over here, at 0, my cubic term has no slope at 0, but this term has positive slope, the mu x term. And so over here, this has to look something like this over here. Right? And so my function then has to look something like this, which goes down, comes back up, and then goes down again. Right? So this is the different kind of things that I can get. Okay, let's just talk about the stability now. This is going to be a stable fixed point. As you can see, the slope is negative. This is once again some fixed point of marginal stability. And here now, this has now become an unstable fixed point at the cost of two stable fixed points appearing. Right? Okay, so let's just think of this intuitively for a moment, and then I'll give you some neuroscientific relevance for this pretty soon. So let's also just draw the bifurcation diagram just to complete the way we've been thinking about these systems, where once again I look at my fixed points as a function of the parameters that describe my system, which in this case is again mu. Right? What do I get? For mu less than 0, I have a single stable fixed point. This fixed point loses stability for mu greater than 0. And instead, I have two other stable fixed points emerge. Hopefully, you can convince yourself later that this will look like some kind of quadratic-like thing over here. Right? So this is what's called a pitchfork bifurcation, because this kind of looks like a pitchfork. Right? You can see that, okay, I don't know how many of you have seen pitchforks, but I guess this is what a pitchfork looks like. And okay, so here you have an interesting kind of thing where as I vary my parameter mu, I have a single fixed point that changes its stability at the cost of the emergence of two other fixed points. Right? So when something like that happens, this is basically what's called a pitchfork bifurcation. Now, one could ask, like, what is the point of a system like this? Where might a dynamical system like this be relevant, right? And so I'm going to kind of describe this a bit more abstractly first. Broadly, the way to think about it is that you can think of this region over here, as being a region where you can take decisions, right? So it's like for mu less than 0, I am uncertain about what choice I want to make. For mu larger than 0, this not making a decision is a very unstable state. This dynamical system can help me describe a context where I can either choose to make choice number 1 or I can choose to make choice number 2. Right. So actually you can model neural dynamics that are related to like decision making. So one example, so very broadly, this is a whole class of what's called like two choice decision making. And you can essentially see that whenever you're thinking of some sort of idea of making decisions between two choices, and this can be in like very complicated context. Like I can say that I want to train some machine learning model that will take in some video feed of you traveling on a road and wants to try to estimate, I don't know, is it summer or winter, right? Okay, some you can train some complex machine learning vision model. What would a machine learning model like that do? It'll keep accumulating information as it sees from the video feed, and it'll gradually try to use that to make a decision. And so if you actually peer into systems like this, you try to analyze the dynamics of the kind of decisions that it makes, you'll oftentimes find pitchfork bifurcations there all over the place, where it's essentially trying to decide, make one choice among two different possible choices. Right. And so really there are a lot of different contexts in which you can model this, or in which you can think about this. And so one example that I want to give that I really like, but I won't spend too much time about this into going into the details, because this is again a whole, it's a wholly interesting problem of its own. This is called, what is called ocular dominance columns. And so the idea essentially is that when we look at objects in the visual field, right, the part right in front of you, right, the part of your fovea that you use to read, that goes into both hemispheres. So some of you might know that, okay, inputs from one eye go into one hemisphere and inputs from one eye go into the other hemisphere. Your brain is kind of cross-wired in this fashion. Your right hand is controlled by your left hemisphere. Your left hand is controlled by your right hemisphere. You have different kinds of cross-firings that go on. But actually the part that is right in the middle of your visual field, the fovea, actually goes to both hemispheres. Okay. And so what I can ask basically is, if I'm looking at regions near this fovea, and I look at one given hemisphere. So maybe let me frame it the other way around. Any given hemisphere is actually now receiving inputs from both eyes at the fovea, right? It's essentially an equivalent thing, right? And so you can ask, if I take any given hemisphere, which neurons are receiving input from which eye? This is essentially now a developmental two choice forcing task, two choice decision making task, where in the developmental context now neurons have to decide which eye are they going to be receiving inputs from. And so this actually gives rise to what are called ocular dominance columns. This is this very crazy experiments that you can do. And so what essentially you're seeing over here is that this is now a small region of your visual cortex, the part of your brain that processes visual input. Black color is representing inputs coming from one eye, and white color is representing inputs coming from the other eye. And you can see this nice patterning that starts to form as different neurons make different decisions. It's a whole interesting space of its own. I'll just point you towards just one paper over here, for example, that kind of shows how this entire spatial patterning can be thought of as some kind of pitchfork bifurcations and two choice decision making tasks that are happening at different neurons in the brain. Right. So you can really arrive at thinking about these things very broadly. As I said, once I give you a normal form, all sorts of different things are going to reduce down to this normal form under the right set of approximations. Whether that is thinking about which neurons are receiving inputs from which eyes, or that is thinking of how does a machine learning model identify, what scenery it's observing, right? Different kind of things. Yet if I simplify the equations, I do the right kind of Taylor approximations, and I do a right kind of change of variables, all of these kind of reduced equations that look something like this. Right.
Sarthak, there's a question.
Yes.
You mentioned the decision-making model for the pitchfork bifurcation. But in these two alternate first choice models, especially something like the drift diffusion models, you have accumulation of evidence. Where is that happening in this, like in this framework?
Yeah, so one way to think about that accumulation of evidence is you can kind of think of that accumulation of evidence as doing two roles. One is that, okay, if you start off at this stable fixed point, if I am strictly on the stable fixed point, then, well, I'm not going to end up making any decision. I kind of need to perturb me either upwards or downwards, right?
Yeah.
So the goal of what the evidence accumulation is doing is to kind of move me forwards or backwards. But the other aspect that's happening as I accumulate more and more information, that is kind of thinking of increasing mu. The reason I say that is because if I'm very close to this bifurcation point, you can imagine that, yes, this is stable over here and this is unstable over here. But if I'm very close to mu equal to 0, it's very weakly unstable, right? In the sense that with perturbations, it's easy for me to kind of hop over this unstable fixed point, right? With small inputs. As I increase mu, that becomes harder and harder, right? So that is like as I accumulate more evidence, initially I have more freedom to kind of pick which side do I want my perturbations to take me. And as I accumulate more and more evidence, it's kind of like also pushing me towards larger mu, which kind of is like solidifying this evidence that I'm accumulating into one of the two decisions. That's like the qualitative picture of where how you can think of evidence accumulation when you kind of simplify those things down to this normal form.
Yeah, I had a related question in the transcritical vibe. What is the physical relevance of mu there, like in the fraction of active neurons model?
So here my mu was just lambda minus 1 over lambda, right? So if I think of lambda as being some 1 plus epsilon, then mu is basically just approximately epsilon, right? Like, or let me put that on. Let's write it another way, maybe. You can think of lambda as being approximately 1 plus mu, right? So, okay, so what does that basically mean? So mu being less or greater than 1 is about lambda being greater or less than 1, which is essentially related to the fact, as I was saying, it's this proportionality constant. It's essentially saying how easy is it for my growth to continue to spread.
Yeah.
Right. So larger and larger mu, that is to say that as mu exceeds 1 and goes higher and higher, it's just saying that it's more and more easy for activity to spread as long as I have availability. It just the growth rate is very fast.
Yeah.
Does that make sense?
Yeah, that got it.
Yeah.
Yeah, so considering any normal form similar to the one you explained now, where it's mu x minus x to the power of n, if my n is if my n is just an odd number, do I always have some sort of like choice in my bifurcation diagram?
Yes, that's a good question. So if I were to instead have x to the power 5, then you can see geometrically you'll get something similar, right? And so in a sense, you're getting the same thing.
So does the number of
And
choices change?
does the number of choices change? Well, not really, in the sense that if I just had mu x minus x to the 5, hopefully you can see intuitively the geometrical picture remains the same, right? If I have just plus x minus x to the 5, my roots are still going to be 0 and plus minus 1, right? So I only have this unstable fixed point and two stable fixed points. Okay, so what happens if I want to make a choice between more tasks, right? Then I actually need not just x to the power 5, but I need some more a polynomial over here that has multiple roots, right? But okay, but then you might ask, okay, why have I kind of only described this level? Even if you consider those multiple roots and you consider modification of things through a single bifurcation parameter, you'll actually find that if you just zoom in, unless you do some extreme fine tuning where all of the roots change their stability simultaneously, what will actually happen is that you're kind of going to be making lots of different either pitchfork bifurcations or some pitchforks and some saddle nodes and things like that. So actually, it turns out, and this is going to be beyond the scope of this course, is that all kinds of bifurcations you can describe, if you zoom in enough, will kind of fit into one of these three categories that I've told you about: transcritical, pitchfork, or saddle node. And so even if I set up something which is an n-choice decision-making task, which is with some more complicated polynomials, I either need extreme fine-tuning, which happens for a vanishing set of parameter values, or I can actually think of that as multiple pitchfork bifurcations, or a pitchfork and a saddle node, or a pitchfork and some transcritical bifurcations.
Okay, thank you, sir.
But yeah, that'll be a little out of the scope for me to really be able to like sketch out examples for you in this course. Are there any other questions? Any other on Zoom as well? Because I'm going to kind of switch gears. So there's something on Zoom as well that should be brought up. Oh, I guess I can also take a look at the things on Zoom because I'm here. Okay, on what factor mu depends, I guess I just answered that. What do you mean by collision of fixed points? So this, I just meant this kind of qualitative picture for what happens as I vary my bifurcation parameter. This is, I guess, language that you'll find very frequently in the dynamical systems world, where as I vary my bifurcation parameter, I think of these fixed points moving about and, kind of like the dynamics of those fixed points themselves. And so by collision, I just mean that, okay, as I increase I have a stable fixed point over here and unstable fixed point over here. As I keep increasing I, these 2 points kind of like collide over here and vanish. Right, you can see in this geometrical picture as well. These 2 fixed points, as I increase I, just collide and vanish. Or over here, they collide and exchange stability. Right, that's what I kind of mean by this qualitative notion of colliding of the fixed points. Are there any other questions?
People have just asked, can you share a reference textbook list?
I will share my slides. It's over here. I will share my slides. So yeah, you don't have to copy it. I will I will talk to the organizing team to get the slides shared today itself. Both the today's slides and Monday slides.
And this activation or activation and deactivating type question has been asked already. And there was, where do we see these among neurons?
Well, okay, I guess that's the kind of question where it's difficult to answer without the context. Whoever asked that to you, would you like to clarify? You can unmute and clarify. What do you mean by what part? Where do we see what in neurons? Oh, neuronal avalanches. So you can see neuronal avalanches in regions of the cortex as well. So this particular experiment, okay, to be fair, this particular experiment was done on a cortical tissue that was grown on an array. So this is not inside the brain, but this is where you grow neuronal tissue outside of the brain. But you can see avalanches and avalanche light dynamics in cortex. That's absolutely a thing. And then how close you are to, this bifurcation parameter of lambda equal to 1 or mu equal to 0, this actually has certain relevance in terms of the kinds of information you can represent and the range of information you can represent, how much information you can encode and so on. So you can absolutely see this in the brain as well, in many areas of the brain actually. So I would certainly advise you can take a look at this paper, or there's another paper, I want to say by Shrew et al. I think 2011, but I could be wrong. I'll add the correct reference to the slides before I share them, which actually tells you more about where you see them in the brain and what the functional reason that they might have in the brain as well, like why you might want some sort of avalanches in the brain. I'll add the reference before I share the slides.
So am I audible?
Yeah.
One doubt. So when you discuss the ocular dominance columns,
Yeah.
So this pattern, it's signifying the exact pattern of the neurons that are present in the brain, is it?
Um, so there are neurons everywhere. This is not the patterning of where the neurons are present. This is the patterning of which neurons get inputs from the left eye versus the right eye.
So is there some kind of deterministic pattern in which they are growing, or is this kind of stochastic?
I believe I guess I'm reasonably certain in saying that it is stochastic. In that this is coming from this is a developmental process, and this is the exact patterning depends on certain microscopic fluctuations in this developmental process. That would be my best guess. Um, there are various aspects of, I mean, this comes down to this whole aspect, like, okay, how much of development is also hardwired versus how much of it is coming from more like activity dependent processes or more like dynamical processes. I'm reasonably certain saying that this is coming from a dynamical process rather than some genetically pre-wired process.
All right.
So I had a doubt in the case of two choice decision making. So,
Mhm.
for example, if we here the bifurcation is happening at a point of mu is equal to 0. So
Mhm.
if we look before that, so the network has some random initialization. So still it will give values to example to inputs. So it will assign 1 and -1. So is it the case that before mu less than 0, the space of assignment is very like discontinuous in nature? So suppose one example, it is giving 1, and if I do some small perturbation, it is still it changes its output to -1. So
So the idea is that for mu less than 0, it's not yet started to make a decision. So it's sitting at just x star equal to 0. So it's just sitting at 0, which is kind of like it's not gotten any information to make a decision yet. Then later, once it starts to accumulate evidence, it then ends up actually making some decision about whether you want to go left or right.
but before even taking any evidence, so so the network will be randomly initialized. So it will have some prior belief about the information. No, so
So you're talking about like if I think of this like what a machine learning model might do.
yes.
So okay, so that kind of depends on how you train the model. You can absolutely train a model to kind of only output the decision after it has iterated for some number of steps. That depends a little bit on the nature. Yeah, if I just were to do it, train like just a feed forward classifier, then I agree that you're right in that it will give you something even before it's done any training or any learning. But you can absolutely train like more complicated decision making model, like some sort of RL based decision making model, um, where it'll accumulate evidence for some number of cycles, or even if you just do a recurrent neural network based decision making model, where it'll essentially won't give you the output for some number of cycles, and then you can have some flag variable that okay, after it's accumulated certain amount of evidence, then it actually stops when this flag variable goes up or something like that.
and
Yeah, so I agree that in a class simplest possible feed forward network, perhaps it will have made some decision here as well before you get any evidence. But okay, you can certainly build more complicated models that will be able to do this much better and will be which are closer to this pitchfork kind of ideas.
I have a related question.
Mhm.
If in the decision making process, if there's a predefined bias that is present in the model or the animal, how would you like change this equation to sort of incorporate that? Like basically, maybe a similar level of perturbation on one side affects more than the other, something like that.
Yeah, so that's a great question. Um, I I'm wondering if I can just point you to the book for that, but I don't remember which chapter it is in. But let me give you the quick answer. Uh, the quick answer is the following. Right now, my bifurcation diagram looks like this, right? I have this, something like this. Now, if I want to introduce some bias into my system, I can think of that as adding, so this was x dot is equal to mu x minus x cubed. I could add some term over here. Let's not, some f of x. Let's not worry about the details over here. And let's say I want this to model some bias. So what you can essentially argue is how adding perturbations can actually change this bifurcation diagram to instead break up into a saddle node bifurcation and no bifurcation. So this branch over here, this part over here is just a saddle node bifurcation. You can see I have no fixed point, which becomes an unstable fixed point and a stable fixed point. And this branch over here is just, it's not undergoing any bifurcation. Right? So this is kind of modeling a bias, which is to say that if I just started off right, before I made any decision, a priori, I'm most likely to just follow on this trajectory. But of course, if I am accumulating evidence, I can eventually jump to this trajectory, but it is just slightly more work than just, I need slightly stronger perturbation than just continuing along this path. So at a geometrical level, this is what the bifurcation diagram changes to. You can have bias basically emerge in these two different kinds of fashions, depending on which side you're biased towards. And then you can argue that this actually happens with almost any kind of perturbation as well. So this is a geometrical picture, and hopefully that is good enough to kind of give you the intuition for the dynamical systems perspective.
Yeah, good.
Okay, so I think then let's move on to the next topic. So we've kind of just given a bunch of examples for what you can do with one-dimensional systems. We have like, I guess, 15-ish minutes. So let me now at least start off the topic of thinking now about 2D flows. Answer what do I mean by 2D flows? So now I have two variables. So I have some x dot and some y dot. And this is equal to some f1 of x comma y, and this is equal to some f2 of x comma y. Right? And hopefully, one thing that you might be now looking forward to is, can I set up a better neuronal spiking model, something that can actually do resetting and so on without needing artificial resetting or artificially making my variable circular. And so that is something that you can keep in your mind as motivation for what we're going to describe. But first, let's just say something a little bit more generally about what can you get in these kinds of systems, right? Okay, I'll just also write this as x dot is equal to f of x. Okay, I guess I'll flip-flop between vector notation and the scalar kind of notation. So one thing to think about now is, now if I think of now my xy space. So this is now my xy space. Every point in space is basically giving me a vector. Right. This is the vector that is telling me how things flow, which basically means that I can draw like trajectories. So any given point will undergo some sort of trajectory based on what the dynamics look like. Right. So at any point over here, if I ask what is f of x is just going to be tangent to this trajectory of this part of this whatever particle in this motion or whatever this dynamical system is doing. Right. Okay, so let's just get to some quick preliminaries. First of all, is it possible for my dynamics to do something like this? Is this possible? Hopefully, you can intuitively see the answer is no. Quick reason is just because if I'm at this point, I need my f to both point tangent to this and be tangent to this. Sorry, let's just do that in a different color. If I'm at this point, I need my f to both look like this and to look like that, which is not possible. So at any point, my tangent vector can only be one vector, and so I cannot have self-intersections. Okay. I can, of course, have closed loops. That's not a problem. Yeah, well, okay. That's essentially all you kind of need to know as preliminaries in terms of what you can and cannot do for the dynamics. So hopefully just with this kind of intuitively, you can see that if I have any dynamics in the plane, so earlier we talked about for the case of 1D flows, I could either go to a fixed point or I could go to infinity, or I could go to minus infinity. Once again, we can do the same thing over here. I can either fly off to infinity, right? So first option is again, go to infinity. Of course, this is now infinity in any possible direction. Or I could basically go to a fixed point, right? So my flow can absolutely just end at a fixed point. Oh yeah, I guess I should also just quickly point that out. Okay, so we cannot get intersections of dynamics, right? So I said that this is not possible. But is this all right? If I have a fixed point, then that's fine, right? So I can have intersections of my flow lines as long as they're intersecting at a fixed point. So certainly I can go to fixed points. I could go to infinity, or I could go to a periodic orbit. Okay, there's essentially this is qualitatively all I can do because my trajectories can't intersect, so it really simplifies what I can do. There is some slight more nuance to this that I won't get into, but I will leave you towards looking at. I'll just tell you what this is called, and then you can look this up in. I think this is there in all of the textbooks that I pointed out. Any of the textbooks you can look for this topic. This is what's called the Poincare-Bendixson theorem. And this basically tells us that, okay, trajectories are going to kind of be, well, simple. Yeah, and so, yeah, definitely look into this for some more nuance about these statements and what they mean about the space and so on. Okay, the next thing I can say is that if I have x dot is equal to f of x, we can do what we talked about earlier. We can say that I'm interested in fixed points, right? So once again, fixed point is when x dot is equal to 0, which means that I have f of x star is equal to 0. If f of x star is equal to 0, then this is going to be a fixed point. In the 1D case, if you recall, we had the same idea. So we had that f of x star equal to 0, and we said that if f prime was greater than 0, then we got an unstable fixed point. And if f prime was less than 0, then we got a stable fixed point. Right? What is the equivalent of that over here? The equivalent of that is essentially what is called what is the Jacobian. So how do I use the Jacobian? Also, okay, so the way we kind of arrived at these equations over here was we did a small perturbation theory. We said, let me assume that x is equal to x star plus epsilon. And then we said that we get epsilon dot is equal to basically f prime times epsilon, right? And so I got some exponential growth or decay. So I basically took my nonlinear system and I reduced it to a linear system. So we can do the same thing over here. If this is a nonlinear system, if I once again say that my x is equal to some x star plus well, some x, okay, let's write it slightly differently. Let's say yeah, okay, whatever. Yeah, x is equal to some x star plus epsilon. I can then go to some epsilon variables, right? And I can then reduce this to some linear system again. And so what will that look like? So I'll once again leave you to it in terms of actually plugging in your Taylor approximation. Hopefully, once again, if you've done your ODEs and your PDE courses, but at least an ODE course, it should be straightforward enough for you to be able to argue this out. But basically, what you will get is that my linear approximation of the system is going to look like let's write it as epsilon. Okay, I'm just going to call this xy as well, but this is now going to be my linear system. So my x dot y dot is going to be equal to this Jacobian, which is basically del f1 by del x, del f1 by del y, del f2 by del x, del f2 by del y, this acting on xy. Right? So this is what the equivalent linear system will be. This object over here is the Jacobian. And this is essentially the generalization of f prime, but now pushed to one extra dimension. Okay. Now, what is the equivalent of asking f prime being greater than 0 or f prime being less than 0? Does anyone have any guesses for what that would mean in the context of now this Jacobian? I guess in interest of time, let me just answer my question myself. It's essentially going to relate to the eigenvalues of the Jacobian. Right? And so I have a 2 by 2 matrix. So it will have some two eigenvalues, lambda 1 and lambda 2, right? And so what I can essentially now say is that I will get a stable fixed point if and only if both lambda 1 is less than 0 and lambda 2 is less than 0. Right? This is kind of like saying that, okay, I have two eigenvalues, they have two eigenvectors. If I have stability in both along both eigenvectors, then I am stable. In all other cases, I am unstable. Right? All other cases. Which is to say that if even a single one is positive, then that's going to be unstable. I don't need both of them to be positive to get instability. Okay. Okay. So this is essentially how I would then go about characterizing the stability of fixed points in a two-dimensional system, essentially by writing out the Jacobian and then by computing the eigenvalues. Now there actually ends up being a trick to kind of do this slightly more easily, which is essentially the following. So let's say that my Jacobian was just some matrix A, B, C, D. Okay. So this is essentially a trick that works in 2 by 2 systems. So, okay, how do I find the eigenvalues? The eigenvalues I can find by saying that determinant of lambda times the identity matrix minus J is equal to 0, right? Which is to say that determinant of lambda minus A, B, C, lambda minus D, this is equal to 0, right? Okay, so if I just actually multiply this out and just collect all the terms, what you'll actually find is that you get lambda square minus A plus D lambda plus AD minus BC is equal to 0. I encourage you to write this out to just ensure that this makes sense to you. And so hopefully what you can also see over here is that this term over here is just the trace of the matrix. And this term over here is just the determinant of the matrix. Right. So okay, so let's just call the trace of J, we'll call that T. Let's call the determinant of J, we'll call that delta. And so then this entire equation just reduces to lambda square minus T lambda plus delta is equal to 0. And then this, okay, I can of course solve. I know that this just tells me that lambda is equal to T plus or minus square root of T square minus 4 delta upon 2. Right? Okay, so one thing that we should note over here is that, of course, because I have a square root thing going on, my eigenvalues can be imaginary, right? Or they can be complex. And so then I need to then clarify, what do I mean by lambda 1 being less than 0 or lambda 2 being less than 0 for a complex number, right? It'll turn out that the only thing that is relevant is really just the real part of these eigenvalues. And so what essentially it comes down to saying is that I need the real parts are both negative to actually give me some kind of stability. Others, I'm going to just have some sort of instability. Okay. I think this is probably a good point to pause. Next time we'll just kind of quickly see what kind of intuition we can draw from this kind of expression. and then we will use that to kind of write out some now neuroscientifically relevant two-dimensional dynamical systems, and we'll hopefully be able to close that loop and give you something that will go up and come back down, actually give me some sort of periodic activity now that I have this extra dimension. Okay. So I guess, yeah, this is probably a good time to pause. If people have any questions, then we can take up a couple of more questions.
There are no questions.
Okay, sounds good. I will try to get you to have access to all these slides. And then we'll pick up with thinking about two-dimensional systems from next time.